Two faint red dots appeared in a James Webb image and looked like galaxies from less than 200 million years after the Big Bang. But when astronomers checked them again a year later, the dots had moved sideways across the sky. How did motion kill the first story? Galaxies at the edge of the universe sit so far away that they should stay frozen in the same position for millions of years. Yet these two objects drifted 15 milliarc seconds in 377 days. That single shift proves they cannot be distant galaxies at all. Instead, the strongest explanation points to cold, failed stars inside or near the Milky Way whose methane-rich chemistry fakes the same infrared signature as hydrogen from cosmic dawn. By the end, you will see why the edge of the observable universe now depends on checking motion, not just color, and why 1 pixel of drift can collapse a record that took years to build. The old method said if an object vanishes in certain filters and glows bright in others, it must be an early galaxy pushed into the infrared by extreme distance. The new contradiction says those same color patterns can also come from brown dwarfs. So cold, they shine only in the bands James Webb was built to see. Here is the first checkable sign. Any object that moves detectably in 1 year of Earth orbit cannot be billions of light years away, because perspective shift from our sun only reveals nearby neighbors. That motion test is the reality check the first interpretation missed. The two red dots sat in a deep James Webb exposure aimed at empty sky, far from bright foreground stars. Astronomers ran the standard dropout test, which looks for objects that disappear in blue and green filters but light up in red and infrared bands. The logic is straightforward. Hydrogen in a distant galaxy emits light at a specific wavelength. But if the universe has expanded enough since that light left, the stretching shifts it all the way into the infrared. When an object passes that test and shows no trace in shorter wavelengths, the usual verdict is high redshift, meaning extreme distance and extreme age. These two dots passed perfectly. They were invisible in every filter shorter than a critical threshold, and bright in the reddest channels Webb can detect. The initial distance estimate placed them at a redshift above 16, corresponding to light that traveled for more than 13 billion years. If true, they would have been among the oldest galaxies ever recorded, shining when the universe was still in its first 200 million years. That interpretation made them instant candidates for cosmic dawn, the era when the first stars ignited and the first galaxies began to form. But the dropout method measures color, not distance directly. It infers distance by assuming the only thing that can produce that specific color pattern is cosmological redshift. That assumption works almost all the time, but it has one hidden failure mode: local objects with unusual chemistry. Brown dwarfs are objects too small to sustain hydrogen fusion, so they never become real stars. They cool over time and eventually reach temperatures below 1,000 degrees, entering a phase called the T-dwarf class. At that temperature, methane forms in their atmospheres and absorbs light at specific wavelengths. Those absorption bands sit in the near-infrared, exactly where Webb is most sensitive. When methane removes chunks of the spectrum, the remaining light creates a color signature that looks nearly identical to a Lyman break, the feature astronomers use to identify distant galaxies. The Lyman break happens because hydrogen gas in the early universe absorbs all light shorter than a specific rest wavelength. When that break gets redshifted into the infrared, it produces the same dropout pattern: invisible in blue, bright in red. Methane in a cold brown dwarf does the same thing for a completely different reason. The two signals are nearly indistinguishable if you only measure color. That is the first contradiction. The old model predicted that any object passing the dropout test and showing no short wavelength light must be a high redshift galaxy. The new evidence shows a local brown dwarf can fake the same test result because methane absorption mimics hydrogen absorption after cosmological stretching. The reframe is immediate. Color alone cannot tell you whether you are looking at cosmic dawn or a cold neighbor. The second anchor contradiction came from the follow-up image. Astronomers re-observed the same field 377 days after the first exposure. When they compared the two images, the red dots had moved. The displacement measured roughly 15 milli-arcseconds, a distance smaller than the width of a human hair, seen from across a football field, but Webb's instruments are precise enough to measure it. That motion is the deal breaker. If the dots were truly galaxies at redshift 16, they would sit more than 13 billion light-years away. At that distance, the only motion visible from Earth would be cosmological expansion, which shifts wavelength but does not move an object sideways across the sky. Proper motion, the term for sideways drift, requires the object to be close enough that Earth's changing perspective reveals a shift. The maximum distance at which Webb can detect proper motion in 1 year is roughly a few thousand light-years, and even that requires a fast-moving star. 15 milli-arcseconds in 1 year implies the objects are almost certainly within the Milky Way, or just beyond it in the local group. The old model said galaxies at cosmic dawn have zero detectable proper motion on human timescales. The result showed clear motion in less than 1 year. The only explanation that fits both the motion and the color signature is a nearby object with methane-dominated chemistry. That means brown dwarfs. The third loop tightens the case by showing what happens when you combine the two clues. The dropout test alone gave a distance estimate of more than 13 billion light-years. The motion measurement alone gave a distance estimate of a few thousand light-years at most. Those two numbers cannot both be true. One of the measurements has to override the other, and motion is the harder constraint because it comes from geometry, not inference. You can fake a color signature with unusual chemistry, but you cannot fake a perspective shift. The angular displacement caused by Earth's orbit is a direct consequence of the object's distance. If the object were truly at cosmological distance, no amount of chemical trickery could make it appear to drift sideways. The motion measurement forces the conclusion. The objects are local. That conclusion immediately explains the color. If they are T-type brown dwarfs, their methane absorption naturally produces the dropout pattern. The mystery is not why they look red. The mystery is why the dropout test failed to distinguish them from real distant galaxies. The answer is that the test was never designed to separate methane from redshifted hydrogen. It was designed assuming local contaminants would be rare and easily ruled out by brightness or clustering. These two dots were faint enough and isolated enough to slip through. The fourth loop shows the scale of the mistake. If the initial interpretation had held, these objects would have been used to calibrate models of early galaxy formation. Their brightness would have implied that galaxies in the first 200 million years were more luminous than expected, which would have suggested faster star formation or more efficient gas cooling. Entire theoretical frameworks adjust when a new distance record appears, because each record shifts the boundary of what the early universe could do. Removing these two objects from the distant galaxy census does not just delete 2 data points. It removes the most extreme examples, which were pulling models toward faster timelines, and higher luminosities. The correction brings the census back towards slower, more gradual assembly. That is the methodological significance. One false positive at the edge of the sample can distort the entire interpretation of cosmic dawn. The fifth loop addresses the broader population. If two brown dwarfs fooled the dropout test in one deep field, how many others are hiding in the catalogs? The Milky Way contains billions of faint stars and brown dwarfs, and Webb's infrared sensitivity makes it better at finding cold objects than any previous telescope. Every deep exposure aimed at distant galaxies will also capture foreground objects, and the faintest of those objects will be the hardest to distinguish. The standard practice has been to use brightness and clustering to filter out stars. But brown dwarfs in the outer halo or in the space between galaxies can be isolated and faint enough to pass those filters. The only reliable way to catch them is repeat imaging. If an object moves between two exposures taken months apart, it cannot be a distant galaxy. That test is simple, but it requires patience and telescope time. Most early Webb observations were single epoch, meaning no follow-up check. The result is that the current census of high redshift galaxy candidates almost certainly contains more local impostors. The exact number is unknown, but the existence of even one confirmed case proves the contamination is real. The sixth loop explains why this matters for the Big Bang timeline. The first galaxies are expected to be small, faint, and rare. Every confirmed detection pushes the boundary of when galaxies could form and how quickly stars assembled. If some of those detections are actually brown dwarfs, the real boundary sits later, and the real galaxy population was smaller. That changes the story of reionization, the process by which the first stars cleared the hydrogen fog that filled the early universe. Reionization models depend on knowing how many galaxies existed at each epoch and how much light they produced. Removing false positives reduces the total light budget, which means reionization might have taken longer or required more galaxies than the contaminated census implied. The stakes are not just academic. Reionization is one of the last major unsolved problems in cosmology, and the answer depends on accurate galaxy counts. The seventh loop shows what the proper motion test actually measures. When Earth orbits the Sun, our viewing angle shifts by 2 astronomical units over 6 months, roughly 300 million kilometers. That shift creates a tiny parallax for nearby stars, making them appear to wobble back and forth relative to distant background objects. The closer the star, the larger the wobble. For objects more than a few thousand light-years away, the wobble becomes unmeasurable even with Webb's precision. The 2 red dots showed a displacement consistent with parallax from objects a few hundred to a few thousand light-years away, well within the Milky Way. That measurement is independent of any assumptions about chemistry, redshift, or galaxy formation. It is pure geometry. The old explanation required the objects to sit at a distance where parallax should be 0. The measurement showed parallax large enough to detect in 1 year. The only resolution is that the distance estimate from color was wrong. The eighth loop closes the case by naming what the evidence eliminates and what it leaves open. The evidence eliminates the possibility that these 2 objects are galaxies from cosmic dawn. The motion is incompatible with cosmological distance, and no amount of gravitational lensing or exotic astrophysics can make a distant galaxy drift 15 milliarcseconds in 1 year. The evidence strongly supports the brown dwarf interpretation because methane chemistry naturally explains the color, and local distance naturally explains the motion. What remains open is the exact subclass, temperature, and mass of the objects, which will require spectroscopy to confirm. The broader question is how many other candidates in the Webb catalog are also local impostors? That number is still unknown, but the existence of this case proves the problem is real, and the solution is repeat imaging. The final reframe is this: the edge of the universe is not drawn by one dramatic image. It is drawn by combining color, motion, and time. A single snapshot can suggest cosmic dawn, but only a second look can prove it. The two red dots look like the oldest galaxies ever found until they moved, and that motion turned a cosmology breakthrough into a brown dwarf detection. The lesson is not that Webb failed. The lesson is that the universe is full of objects that can fake the signals we look for. And the only way to separate the real from the fake is to check whether the story holds when you wait and look again. The old method trusted color. The new method demands motion. That shift does not just change how we find distant galaxies. It changes how we define the boundary between here and the beginning of time.